Hello, everyone. This is chapter 12, Equilibrium and Elasticity. Um, Today in this lecture, we're going to cover those two topics. I think you're going to find they're much easier to understand and master than what we were previously doing last week. Um, so let's get started with equilibrium. So you need to understand that when we talk about equilibrium, we're only talking about static equilibrium. What that means is we're talking about systems that are neither rotating nor translating, moving in the X or the Y or the Z direction. So there's no translational motion and there's no torque. Um, and we're going to define them mathematically. I think you're going to find that the math is particularly simple. It ends up being a lot of tedious algebra. The hard part is actually the physics. Being able to analyze the system and figuring out what the torques and what the forces are that are affecting your system. And there's a few little pitfalls I'm going to go through. So how I'm going to do this is I'm going to define equilibrium, and then we're going to do 3 examples that get increasingly more complex. And hopefully by the end of the 3 examples, you'll have a pretty good feel for static equilibrium. And then we'll move on to elasticity, and I'll have more to say about that when we get there. So let's define static equilibrium. An object is in static equilibrium if the following conditions are satisfied. And remember that static equilibrium means it's not moving in translational motion and it's not rotating. So if there's no translational motion, then the sum of the external forces acting in each direction, X, Y, Z, of the system is equal to 0. There are no net external forces acting on the system. Secondly, if the object's not rotating, the sum of the net torque acting on the system about any axis of rotation is equal to 0. We'll talk about what that means. That's probably the biggest tool that we have in our arsenal to handle these problems. So as you can see, sum of the external forces is 0. The sum of the net torque is 0. It's pretty simple. It ends up being a lot of algebra, as I said. But I think the easiest way to introduce this is to start with a very simple problem. Before that, we need to recall one major thing that we've been using all semester, and that is center of mass. So imagine you have some weird shape. Let's say it's a ball of clay. So we have some X and Y axis, and we have some origin, and then we have this weird lump of clay here. And it has a center of mass, let's say here, okay? We can treat this whole thing as if it's a particle where it's a particle at the center of mass. Let's imagine that there's a z vector going, it's a negative z vector going into the page and a negative z vector coming out of the page, or a positive z vector coming out of the page, and about any axis of rotation. So about the z-axis, about the y-axis, and about the x-axis, about any of those axes, there is no rotation. And secondly, there's always a weight vector that will be mg coming away from it. So for every piece of mass in the system, we're going to have a weight vector. That's probably the most important thing to remember. The other thing to remember is the forces that we defined way back when we talked about Newton's equations. We had weight, which was always equal to mg. We had tensions. We had friction. And in this chapter, we're going to go back to our frictional force as a mu times a normal force, a coefficient of friction times a normal force. We have normal forces. We don't always have normal forces, but sometimes we have normal forces, and that's it. So if you keep that checklist in your head as we go through these problems and you're trying to figure out what forces apply to your system, just run through it. Have you accounted for every weight? Have you accounted for the tensions? Have you accounted for friction? Have you accounted for normal forces? Have you accounted for any other weird force that might be showing up in this problem? We'll talk about a few of those at the end of this too. So let's go into that first the simplest example. Imagine that you have a bar, and it's just a thin, uniform density metal rod, and it's being supported by two wires, one on the left, one on the right. So wire left, wire right, and it has a center of mass exactly at the middle of it. And this whole length is going to be 2 meters, and the entire bar, let's say, weighs 5 kilograms. So the mass of this whole bar is 5 kilograms. And what we want to know is we want to know what the tension on the left and the tension on the right wire are, okay? That's it. We need to come up with what is the tension left, what is the tension right, and the only thing we know is that this bar is held in static equilibrium, okay? So first of all, our mathematical description. In our mathematical description, the first thing we need to draw is a free body diagram, as always. So treating that bar as if it were a point, there's a weight, mass of the bar times g. There's a tension on the left and a tension on the right. And the acceleration is 0, okay? But let's choose this to be our positive y direction, okay? Now, first things first, we know that the forces have to be 0. That means that the sum of the forces in x are 0. There are no forces in the x. But the sum of the forces in the y are t left plus t right minus mg is equal to 0. One other thing I want to say, I'm going to assume that g is 10 meters per second squared. It makes the algebra faster and easier. On a quiz or an exam for me, if you want to use 10 meters per second squared for gravity, I'm fine with that, unless I tell you otherwise. If I specifically tell you that g is 9.81, use 9.81. Otherwise, feel free to use 10. Your answer would be a little bit off from a real answer, but it's okay. So what we have here is we have that t left plus t right is equal to mg. And I said that m was 5. So this is 5 times 10. This is 50 newtons, okay? So we have one equation. T left plus T right is 50 newtons. We have two unknowns though, T left and T right. So we can't solve this yet. And so how we're going to solve it is we're going to need another equation. That equation comes from the other condition of static equilibrium, which is that the sum of the torques is 0. So whenever we have torques, the first thing is what is the axis of rotation? And here I'm going to choose it to be the center of our rod. So we have at the center of our rod, we have our axis of rotation. At a distance, length to the half, we have our tension on the left. And at a distance, length to the half, we have our tension to the right. Don't assign that to be negative T or negative L to the half. It's just L to the half. It's the distance from the axis of rotation. Remember that our L was 2 meters, so L to the half is 1 meter. So what are the torques? What are these two torques? Remember that when we draw a torque diagram, we draw the two vectors tail to tail. And then by the right-hand rule, if it's counterclockwise, it's positive. If it's clockwise, it's negative. This is clockwise, so it's negative. Another way to see this is that this angle is negative 90 degrees. Okay, so we have each torque is R cross F here. That gives us RF sine of the angle between R and F. So for this guy, we would have L to the half times T times sine of negative 90 degrees, which is negative L to the half times T2. Similarly, we have L to the half and I'm sorry, that's not T2, that's TL. I'm being a little crazy. So T to the left, T to the left. To the right, we see that when we rotate our R vector, our L to the half vector, counterclockwise, so we get a positive torque. And therefore, the sum of our two torques is L to the half times TR minus L to the half times TL. And that is equal to 0. The sum of the torques is equal to 0. Those are the only two torques acting on this system. And we get that L to the half times TR is equal to L to the half times TL, or that TL is equal to TR. Divide through by L to the half, you get that TL is equal to TR. So our solution is, using the two equations that we found that TR plus TL was 50 newtons. Secondly, we found that TR was equal to TL. Therefore, if I plug in for TR, TL, I get TL plus TL is 50 newtons, or 2 times T to the left is 50 newtons, or that T to the left is 25 newtons. Therefore, T to the right, which is also equal to T to the left, is also 25 newtons. And we're done. We found our two tensions. We had to find the forces and set them equal to 0, which is what we did here. The sum of our forces set equal to 0 gave us that TL plus TR was equal to mg. And then we had to find our torques about, in this case, we chose the axis of rotation to be the center of the bar. And that enabled us to find that TL was equal to TR, and plugging that back in gave us our answer. However, there's a trick that we have up our sleeve that we didn't use here. Well, we kind of did, but we could have done something slightly different. So we could find the torque about any axis of our system. As long as it's in static equilibrium, it's not going to rotate at all about any point. And there's going to be another point I want to make after this about this. But let's, instead of choosing our center of mass, we'll choose our axis to be on the left. So remember, this is where our left tension was. The bar, which is 2 meters in length, at the center of mass, there is still going to be mg, the mass of the bar times g, and at the very end, this will be TR. So this distance here is 1 meter, and this whole distance is 2 meters, okay? So our sum of our forces, which is still 0 in the y direction, the sum of our forces in the x is of course 0, there's no forces in the x, is TL plus TR minus mg is equal to 0, or TL plus TR is mg, which as before was 50, or 5 times 10, which was 50 newtons. That's still the same, okay? However, now let's look at our torques. And we have R to the mass and the mass times G. And then we also have R to this tension that I'm going to call RT times tension to the right. And of course, right on the axis of rotation, we have the tension on the left, but the radial vector to the tension on the left is 0. So these two torques are going to be R to the mass, which remember is 1 meter. Put them tail to tail. This rotation is clockwise, so it's negative. Then we have R to the T, and we have TR, and this rotation is positive. So the sum of our torques is R, this is 2 meters, by the way, R to the tension times tension on the right, minus R to the mass, mg, and that's equal to 0. So we find that R to the mass, mg, is equal to RT TR, or that TR is equal to mg times R to the T over R to the mass. Sorry. Wow. R to the mass over R to the tension. Then we go to a new page. And so we get that the tension on the right was equal to R to the mass times N times G over R to the tension. Remember that this was 1 meter. This was 5 kilograms. We're going to assume this is 10. And R to the tension was 2 meters. Therefore, we get 50 over 2, or 25 newtons. Going back, TR plus TL is 50 newtons. If TR is 25, then TL is 50 minus TR. TL is 50 minus 25. TL is 25 newtons, which is exactly what we found before. We found that TL and TR were equal, and they were both equal to 25 newtons. So the main takeaway here is that we can choose any axis we want in order to compute the net torque. Sometimes there's going to be a more appropriate place than another. We'll see that when we do the ladder example. But just bear in mind that you can always do it. Sometimes it'll make the math easier. Sometimes it'll get rid of unknowns that you have but you don't want to consider. We'll talk about that later. But there is one last thing that I want to bring up with this simple example, and that is that what if the object isn't actually in static equilibrium? How would you know? So let's imagine our bar again, but imagine instead of 2, and it's still 2 meters long, and we still have this center of mass here at the center at 1 meter, okay? But imagine now at half of a meter, we just have this one tension, and it's 0.5 meters away from the center of mass. So when we do our forces in the y, we would still have T minus mg is equal to 0, because this bar, right, has a tension and it has an mg, okay? And so you would say, oh, well, the tension is just mg, right? But when we try to do the sum of our torques, what we find is our center of mass is where our axis of rotation is, and then at this R, we have this tension. So drawing that torque diagram, we have R, and we have T, It's rotating clockwise, which means this is a negative torque. So the sum of our torque is negative RT, which does not equal 0, which means we have a problem. This object cannot be in static equilibrium unless there's another force causing another torque, which is keeping the net torque to be 0. What actually ends up happening if this is the case is it would end up looking something like this, where basically the tension and the center of mass are opposite each other, and the torque is, well, the tension and the radial vector are parallel, therefore there's no torque. You know that physically. If you tried to hang a stick from the ceiling, it would fall over until it would basically align to the string of the ceiling. So static equilibrium, you have to have enough forces and torques to balance everything. If you get to the point when doing one of these problems where you don't have a balanced equation, an equation that can equal 0 somehow, you've probably forgotten a force or neglected to include a torque. It's one of the things that makes writing these problems a little difficult. But okay, so let's move on to a little bit harder problem. And this is the same idea. We have a thin uniform density rod. I'm now going to assume that this distance is 6 meters and this distance is 6 meters. At this edge, I have a wire that's going to be giving me tension 1. I'm just going to call it tension 1. I'm going to have a mass A that is located at a distance of 3 meters away from the center. So 3 meters away. I'm going to have a second wire, and that's going to be 4 meters from the center. And I'm going to have a second mass B, that is going to be right on the edge there. I know that the mass of my bar is 10 kilograms. And I know that mass A and mass B are 6 and 2 kilograms, respectively. And then I know this distance, I'm going to call R1. So R1 will be 6 meters. This is going to be my RA, and that'll be 3 meters. My R2 is my distance from the center to the wire, number 2, and that is 4 meters. And finally, my distance to mass B is also 6 meters. Okay. And again, I'm going to consider G to be 10 meters per second squared in this problem. Okay. So just as before, our first step is to sum the forces and set them equal to 0. Going through the types of forces, really quickly, I want to talk about normal forces. So imagine you have a bar and you have a mass on top of the bar, little m. I'm going to call this big M. Okay. So there would be a normal force on little m, and there would be a normal force pushing down on big M. So this normal force would be due to big M pushing up on little m, and there would be a normal force on big M from little m pushing down on it. Those two forces are a third law pair. They are equal and opposite, and they cancel. So there are no normal forces in this problem. And the only forces we're going to need to consider will be the weight for each mass, mg, and the tensions. There's no friction in this problem. There's no other forces besides weight and tension, and there are no normal forces in this problem. Okay? So what are the forces? Imagine our system. We know that we have the mass of the bar times G, we have mass A times G, we have mass B times G, we have tension 1, and we have tension 2. The tension of the 2 wires and the 3 weights. So our sum, there's no X forces again in this problem. The sum of the forces in the Y is going to be T1 plus T2 minus M bar times G minus MA times G minus MB times G is equal to 0. And again, I know what all these masses are. So this is M bar times G plus MA times G plus MB times G. And this was 10 times 10 plus 6 times 10 plus 2 times 10. 100 plus 60 plus 20 is 180, so 180 newtons. So the sum of our 2 tensions is 180 newtons, and once again, if we want to know what T1 and T2 are, we don't have enough information to solve this yet. And therefore, we have to turn to our torques. Now, we're choosing our axis of rotation at center of mass. So when we draw this torque diagram, we're going to draw an X for our center of mass. We know that we have RA to MA times G. We also have R1 to T1. We have R2 to T2. And we have R of B to MBG. There is a force here of M of the bar times G, but because it's sitting on the axis of rotation, the radial vector would be 0, and therefore there would be no torque. So the sum of our torques is equal to 0. What is the sum of our torques? So let's go through each torque. Remember that you have to draw them tail to tail, and then check a clockwise rotation. R turning towards the force is negative. A counterclockwise rotation is positive. A counterclockwise rotation is positive, and a clockwise rotation is negative. So you can see here, this torque, R1, T1, tail to tail, rotating R to T1 is negative. RA, MAG, rotating RA to MAG is positive. R2, T2, rotating is positive. RB, MBG, rotating is negative. So the sum of our torques are, each of these torques is 90 degrees off of, or each of these vectors are 90 degrees off. Therefore, RF sine of 90 is 1, and we've chosen the negative and positive signs by the right-hand rule. So we get negative R1, T1, plus RA, MAG, plus R2, T2, minus M, stay consistent, RB, MBG. And that is equal to 0. So let's move the mass terms over and leave the tension terms here. So we get R2, T2 minus R1, T1 is equal to RB, MBG minus RA, MAG. Okay. Now, we have everything we need to solve this. So our solution is that T1 plus T2 is 180 newtons. We got that from our force equation. And then that R1, T1 minus, actually, let me double check. Sorry, R2, T2, R2, T2 minus R1, T1 is equal to RB, MBG minus RA, MAG. Now, we can plug in for T1, 180 minus T2. And when we do that, we get that R2, T2 minus R1 times 180 minus T2 is equal to RB, MBG minus RA, MAG. This becomes R2, T2 plus R1, T2 is equal to, this would be negative R1 times 180, move it over, and we get 180 times R1 plus RB, MBG minus RA, MAG. Note that this is R1 plus R2 times T2, and R1 plus R2 was 12, was 10 meters. If you go back and look here, R1 was 6, R2 was 4. So that's 10 meters. So this is R1 plus R2 times T2 is 180 times R1 plus RB, MBG minus RA, MAG, dividing through by R1 plus R2. R1 plus R2, and we're ready to put in numbers. So this becomes 1. We get 180. Now R1 was 6. 180 times 6 plus RB was 2 times, sorry, that wasn't RB. RB was also 6. MB was 2 kilograms. G is 10. RA was 6 kilograms. I'm sorry, RA was 3. MA was 6, and times 10 again. And then R1 plus R2 was 10. So T2 is equal to 6 times 180 plus 6 times 2 times 10, that's 120. This is 1080 plus 120 minus 180 divided by 10. So this is 1200 minus 180, which is 1020 divided by 10, which is 102 newtons. Okay. Now, if we go back and we remember that we had that T1 plus T2 was 180 newtons, and we just found that T2 was 102 newtons. Therefore, T1 is 180 minus T2, which is 180 minus 102. So T1 is 78 newtons, and that is our answer. T1 is 78 newtons. T2 is 102 newtons. It's a lot of tedious algebra. All of these problems are. The fun part's figuring out the forces and the torques. The annoying part is figuring out all the algebra. And this is actually still pretty simple. We only have 3 masses and 2 tensions. and we've got a page full of algebra. But at least the algebra is relatively simple and easy to do. As before, let's go about a different axis. And here, I'm going to choose to put the axis of rotation at where wire number 2 was. So let's remember this. There was a tension 2 right here. And 2 meters away, we had mass B. And then 4 meters away, we had the center of mass of the bar, right? And then, so this would be 7 meters from T2. We had mass A, and a full 10 meters, we had tension 1. So if I draw this, remember that we've got the center of the bar, we had A, we had T2, and we had T1, and we had mass B, okay, right at the end. And this distance from T2 to A was 7, this distance was 4, the distance between the wires was 10, and this distance over was 2 meters. The sum of the forces about X is still 0. The sum of the forces about Y is still T1 plus T2 minus M bar G minus MAG minus MBG. And this is equal to 0. If the masses are all still the same, we get T1 plus T2 is 180 newtons. That part stays the same. The part that changes is going to be the torques. So let's draw all of our torques. We have, I'm going to call this RB, and my RB is 2M, and then I have the weight of MBG. I'm going to call this R to the center mass. So I have the mass of the bar times G, and R to the mass was 4 meters. And then I have R to A, which was MAG, and R to A was 7 meters. And then lastly, I have R1 to T1, and R1 was 10 meters. So drawing each of these torques, remember tail to tail. So this is a clockwise rotation, which means it's negative. RA, MAG. This is a counterclockwise positive. RM, M bar, G. Whoops. Tail to tail. M bar, G. Also counterclockwise, also positive. And lastly, RB, MB times G. This is clockwise, which is negative. So make sure you understand those torques. You're gonna get plenty of practice on torques with these types of problems. So the sum of our torques is negative R1 T1 plus RA MA G plus RM M bar G minus RB MBG is equal to 0. Remember that those values of RA, RM, RB, and R1 are given above. But the nice thing now is we can move this term over, and so we get R1 T1 is equal to RA MA G plus RM M bar G minus RB MB G. And by dividing through by R1, we get that this is RA was 7, MA was 6, and this is 10, minus RM was 4, and the bar was 10, and this is 10. This is plus, sorry. Minus RB was 2, and MB was 2, and this was 10. And then R1 here is 10. So I get 42 times 10 plus 40 times 10, which is 82, minus 4 times 10 all over 10. This becomes 78 newtons. And if I move up here, so I see that T1 is 78 newtons. And recalling that I had T1 plus T2 is 180 newtons. This shows me that T2 is 102 newtons, which is exactly what we found before. The nice thing about doing it this way is I didn't have to do that initial substitution of T1 and T2 into this problem. So if that helps you, great. There's no really big advantage from doing it here, from changing the axis of rotation to anywhere special. But it works. It gave us the right answer. It gave us the same answer that it gave us before. However, now in our third example, we're going to see the hardest problem of these that we've done so far. And we're going to see where choosing the appropriate axis of rotation actually helps us solve the problem. So this is the ladder problem. It is a problem in your book. I want to say it's 1202. It is sample problem 1202. No, it's sample problem 1203. So in this problem, and I'm going to do a slightly different problem from the one in the book, but it's 99% the same. So in this problem, we have a ladder leaning on a frictionless wall. The ground actually has friction, but this wall is frictionless. The ground has some friction with some unknown coefficient of static friction. And this is at a 70-degree angle. There is a firefighter standing on here. He is at a third of the length up. There is a center mass of the ladder itself is halfway up. Okay. So our job in this problem is to figure out, assuming he's not slipping, that the ladder's not falling at all, what is that coefficient of friction on the ground? And we're going to assume in this problem that the ladder itself is 8 meters long. 8. Sorry. I want to make sure that I use, no, 6 meters long. The mass of the firefighter, which I'm going to call MF, is 60 kilograms. The mass of the ladder is 30 kilograms. Okay, and that's all we know. And the angle, of course, is the angle that the ladder is inclined at is 70 degrees. Okay. So one thing to remember is, again, that the various forces that we're going to consider here are only weight, which is mg. We're going to have one for the ladder and one for the firefighter. We're going to have normal force. We'll talk about those in a second. And we're going to have a friction force. We don't have any tensions because we don't have any wires or ropes. The friction force will be mu times some normal force. We're going to need to figure out what that is in a second. But take a minute and see if you can figure out, there are 5 forces on the system, 5. So see if you can figure out what they are. Pause the video and see if you can guess what they are. And then unpause. So on this ladder is basically our system. It's resting against a frictionless wall. And that means there's no forces up or down. However, there is a normal force in the negative x direction on this ladder. Okay. The next easiest 2 things to do is there is a weight of the firefighter and there's a weight of the ladder. Those 2 are easy. The final 2, though, there's got to be a normal force acting in the positive y direction. And then there better be a friction force, static friction, holding the ladder from sliding. You can also see this because the sum of the forces, first of all, let me say that x is positive and y is positive. It doesn't really matter which direction you say is positive because equilibrium forces, but I'm going to say that that's my x positive. So the sum of the forces in the x, if I had forgotten my static friction force, I would have simply gotten a normal force in the negative x direction. And my static friction force, okay? That's equal to 0. If the static friction force, if I had forgotten it, this wouldn't equal 0, so I would know that there was a force I wasn't considering. Had I remembered the static friction force but forgotten the normal force of the wall, I would have known either way. So the force of static friction is equal to nx, right? But remember that my force of static friction is mu and y, this ny. So therefore, I get that mu ny is equal to nx, or mu, which is what I wanted, is nx over ny. This is what I'm trying to figure out. This is what I need to find, okay? What are my forces in the y? In the y direction, I have a normal in the y, of course, minus the mass of the ladder times g minus the mass of the firefighter times g, and that is 0, okay? So n of y is equal to the mass of the ladder times g plus the mass of the firefighter times g. I said this was 30 times 10 plus 60 times 10, or this is 900 newtons. So I know what ny is. It's 900 newtons. What is nx? How do I find nx? And that's the real problem. The first challenge to doing these problems is making sure that you get all the forces, that you understand on a frictionless wall, there's going to be a normal force perpendicular to the surface acting on the ladder, which is what our nx is. It's perpendicular to the wall. There is going to be a normal force on the floor acting perpendicular to the surface on the ladder, which is our ny, but there's also friction on the floor. Otherwise, this ladder would slide off. The bottom of the ladder would slide off to the left and the guy would fall down. The next part is actually the part where things get a little bit difficult and we really need to talk about forces and torques and how torques work. So I want to do a really brief refresher on something on torques. And that is, imagine that you have a r vector, and this is your axis of rotation, and you have a force applied downward, okay? And we know that the torque due to this force is going to be r cross f, which is rf sine of the angle between r and f. But now that's our problem, because this theta, I don't know what this theta, I know what this theta is, but I don't know what this phi is. So if we look at geometrically, we know in this example that if this is F and this is R, for torques, we always put them tail to tail. This becomes theta plus 90 degrees. So phi is equal to theta plus 90 degrees in that case. This is R cross F, which is RF sine of theta plus 90 degrees. But that's cosine, right? This is RF cosine of theta, okay? Right? You can check that for yourself, but I assure you that it is actually true. Sine of 30 and cosine of 120 are off by a negative sign. So the negative sign we'll figure out by the right-hand rule. However, what's actually going on here without worrying about all the math is something quite simple. And that simple thing is a better way to state force, or torque. So torque, remember, is R cross F, which is RF sine of phi. But a better way to say this is that it is R cross F is equal to the perpendicular part of R to F. So back when we have this R and we have our angle or our axis of rotation and F, we know that from this axis of rotation, we have two vectors. We have Ry and we have Rx, okay? And if this angle is theta, then this is R sine of theta, and this is R cos of theta, okay? And this is still R, R, and this is still RF. Now, we can look at these two, and let's draw a torque for both of them. So from the axis of rotation, we would have Ry, and we would have F. And there is no torque, okay? There's no torque because they're parallel. However, Rx and F do have a torque. In fact, it's a negative torque. So this torque is Rx with a negative sign times F. Well, that torque is therefore R cosine of the original angle times F with a negative sign. Okay? Good enough? What you need to do is break up your radial vectors for these torques into the perpendicular component. We'll talk about each of those as we do each of these torques. Going back to our picture, we have to choose the most appropriate axis. And remember, we have this ladder, we have normal y, we have normal x, we have a normal y, we have a force of static friction, we have an MFG, and we have an MLG. Okay, so where do we want to put our axis of rotation? We can't put it here because we're trying to find NX. And if we put it there, NX wouldn't appear in our equation and it wouldn't tell us anything. So we need to figure, we could put it here, but if we do that, we're going to have 1, 2, 3, 4 torques. If we put it here, though, okay, we actually eliminate Ny and the force of static friction because the radial vector for each of these torques is 0. They are on the axis of rotation. So that leaves us with three torques that we need to figure: the torque of the firefighter's weight, the torque of the ladder's weight, and the torque of the normal force in the x direction. Okay, these are all vectors. Remember that this was L to the third, this was L to the half, and this was L. Okay, and each of these was 70 degrees. All right, so let's look, and which one of these two vectors is perpendicular to the weight of the firefighter? That would be our R vector times cosine of theta. Here again, it would be our R vector times cosine of theta. And here, it would be our R vector times sine of theta. Okay, notice that this R cosine of theta would actually be parallel to n of x, so we don't want to use that part. We're trying, once again, to find the torque is R perpendicular to F. Okay. Lastly, remember that L was 6 meters. So L to the third is 2 meters, and L to the half is 3 meters. And M of my firefighter was 60 kilograms, and M of my ladder was 30. All right, cool. So let's find our torques again. I have basically L to the third times cosine of 70, and the firefighters, this is negative. It is a clockwise rotation. I have L to the half times cosine of 70 times mlg. Again, clockwise, it's a negative torque. And then I have L sine of 70 times n of x, and this is a positive rotation. So the sum of my torques is negative L to the third cosine of 70 times mfg minus L to the half cosine of 70 mlg plus L sine of 70 times n of x, and that is all equal to 0. So I'm going to move to the solution page and rewrite that. So 0 is equal to L to the third cosine. So I'm going to write this a little bit differently. mfg cosine of 70 minus L to the half mlg cosine of 70 plus L times n of x times sine of 70 is equal to 0. So let's move this, all of this stuff over there, and we get L times sine of 70 degrees times n of x is equal to L to the third times mfg plus L to the half times mlg, all times cosine of 70. If I divide through by L sine of 70 degrees, L sine of 70 degrees. First of all, note that there's an L here and an L here, so I get that n of x is equal to mfg divided by 3 plus mlg divided by 2. The L went away from here. Cosine over sine is 1 over tangent of 70, or cotangent of 70. I'm going to leave it as tangent of 70 for my computer or for my calculator. So mf was 60. So this was 60 divided by 2 times 10 plus 30, I'm sorry, 60 divided by 3. 30 divided by 2 times 10 times 1 over tangent of 70. Now, this is 20 times 10, which is 200, and 15 times 10, which is 150. So this is 350, right? Divided by tangent of 70, and I get 127.4. So my n of x is 127.4 newtons. Lastly, remember I was trying to find the coefficient of static friction, and I said that was nx over ny, and in fact, ny was 900. So this is 127.4 divided by 900, which gives me approximately 0.14, 0.14 as my coefficient of static friction. So after all that, the hard part is figuring out what the torques are and making sure that you get the proper perpendicular R vector. Other than that, it's still just setting the sum of the forces equal to 0 and the sum of the torques equal to 0 and using the two equations to solve for what you need. Other variations of this would be the sine problem, which is 1202, I believe, in your book. You'll get a few others. It's not too hard to deal with. It's actually pretty easy. A lot of algebra, a little bit of geometry. Nothing major though. Okay, it actually feels more like we went back to chapter 4 a little bit. So that being said, yeah, we'll probably get some problems on this later in the week that I'll do. We'll do a few more sine problem, maybe something else. But now I want to move on from equilibrium, static equilibrium, to elasticity, which is something that you might be familiar with if you've taken chemistry. It's valuable to engineers. Basically, all solids have a property called elasticity, which means if you try to pull it apart or compress it or bend it, how they respond to that, the length change or the deflection or the compression, which results in a volume change. These experiments have been done on things like steel or wood or plastics. Basically every type of material that is basically a solid. So water is a liquid, and we're going to talk about water. Water can be compressed, but in general, we're talking about solids like steel or lead or brass, tin, things like that. So the first thing I want to state is that this whole part of this chapter, these are experimental results, and you can tell that right away. I'll take you through what those experimental results were. Essentially, what they found was what the proportionality constant between the stress, which is actually a pressure, and the strain, which is a change of length over a total length. They found the proportionality between those two for materials using force gauges. They found that there's a linear relationship at first, and so we're going to assume that there's always a linear relationship, that's what we're talking about, the linear part. Before I go on and explain kind of the experiments that result in some of the findings, I want to talk about the definitions of these things. So stress is defined as a pressure. It's a force over an area. We'll talk about what a cross-sectional area means. We've talked about it before, but we're going to talk about it again. We talked about it briefly when we talked about drag. So we're going to talk about it again and how it applies in elasticity. Strain is the change of length over the total length. So imagine you have a 4-meter long shoelace and you pull it super hard and it becomes a 4.1 meter long shoelace. That would be the strain. The strain would be the change of length, the 0.1 over the 4 meters. We'll talk about that more later. Shear is deflection. So if you bend something, how much it's bent by, and we'll explain that later. over the total length of the object. And lastly, when you apply pressure to a solid, like dropping it in the bottom of the ocean, that pressure compresses and changes the volume. So a compression is a change of volume over a total volume. Those are the things we're talking about. It'll be clearer as we go through these problems. These problems are really quick. They're basically plug and chug. There's a lot more here physically that you can explore later in higher level classes, and chemistry and engineering and thermodynamics. Elasticity is actually very important to engineering and chemistry because solids change their shape based on what's happening to them. Even things like cells change their shape and have a certain elasticity. However, remember that we're talking about solids. And we're talking about a very small linear region of response to pressure or force. And lastly, what I want to say is keep in mind that these are very experimental. There's things like concrete. Concrete actually changes how it reacts to a compression versus a stress. And so some of these numbers are best case, but we're going to go through it and hopefully you'll learn something neat about it. Experimentally, it is what it is. The last thing I'm going to say is we're going to be dealing with very big and very small numbers. You'll see that really quickly. So it's back to that scientific notation stuff. Make sure you know how to do it so that you're not entering 1 times 10 zeros into your calculator, okay? All right, let's talk about experiments and the linear region. So imagine I have a wire and I'm gonna pull on this wire. I anchor it to a wall or something and I start pulling on it with a force, okay? And this wire has a little cross-sectional area, which isn't important right now, but I define that force over that cross-sectional area, and I compute the change of length over the total length. So this is the total length. It gets stretched some little tiny delta L, and I graph force over area, by the way, it's pressure. So pressure is force over cross-sectional area. The pressure I apply, the force over area that I apply, versus the change in length over the original length, and I map it. I simply graph this graph. And what I see is it starts off with a fairly linear relationship, and then it kind of starts to fall back a little bit, and then it shoots up rapidly until it breaks. So at a certain point, when you pull it enough, it breaks, it completely shatters. And for most objects, so this linear region is what we're talking about. We assume that there's a linear trend line that governs that. And so what we get is we get some slope that we're going to call, in the case of shear, your book calls it E. I'll talk about that in a second, but E is going to be your Y over X, or your force per cross-sectional area over your change in length divided by your total length. This E right here, I'm going to put what your book calls them, and then I'm going to put what other places call them here. This E is Young's modulus, and it's the stress, the force over area, divided by the strain, which is the change in length over the length. And it's only this linear region before this weird behavior starts. There's a lot of physics in here. We're assuming that all the physics are in this coefficient E, this unnamed quantity E that gets the name of Young's modulus from the guy who first did it, okay? Similarly, for stress, we have S, as your book likes to call it, And S is the shear modulus, and it's a measure of the force over area divided by the deflection over total length. We'll get to that. We'll go over that more in detail in a minute. And then lastly, there's this, your book calls it B, it's a bulk modulus, and if you apply a pressure, there's a compression until it ruptures in that compression. So S, let's write FA over change of X divided by L, and the bulk modulus is the pressure, I'm just going to call it pressure since we're usually in fluid, over the volume change over the volume, okay? Now, what you should know though is Young's modulus is usually written as Y. The shear modulus is usually written as a shear modulus is usually written as a oh, I'm sorry, and this is actually, your book actually calls the shear modulus G. I think most other things call it big S. And lastly, the bulk modulus is usually this beta. Your book uses a large B. Doesn't matter though, these coefficients are usually given to you or you're solving for them and you know everything else. So really what this boils down to is if you're given, say, a force and a cross-sectional area and a change in length and a length, and you're told to find Young's modulus, or you're given the cross-sectional area and the change in length over the length and Young's modulus for something like steel, and you're asked to find the force. We'll do a couple of those so you see. But the first thing I need to make sure that you remember is cross-sectional area. So in the most common cases, and you can do most of these yourself, I'm sure, imagine that we have a long, thin wire, right? And this long, thin wire, we're going to pull up with a force that's parallel to the wire, right? So this is our cross-sectional area. And if the wire is circular, then the cross-sectional area is pi r squared. It's just the perpendicular area to the force. It's sometimes written a perpendicular. I tend to write it a that so that you remember that it's cross-sectional. So if instead we had like a block, right? And same thing, we're pulling on this face of the block with a force, then the cross-sectional area would be the, right, would just be this, right? So it would be the length times the width. If this was some length and this is some width, it's just the perpendicular area to the force, okay? And we'll always use, in this class, we'll always use solids that have a well-defined cross-sectional area. You need to remember your geometrical formulas of length and width and pi r squared, but other than that, nothing too tough. Usually the volumes that we're going to be talking about will be 4/3 pi r cubed if necessary. But you guys will see that we almost always talk about a fractional volume and a fractional length change. So the last thing I want to say is the fractional change. Fractional change is delta x over x. So if I say delta L over L, that's the fractional length change. If I say delta V, delta L over L, or delta V over V, that's the fractional volume change. Multiply that by 100% and you get the percent change. That's pretty easy. It's like what we've been doing in lab. Okay, so let's put this into action. We have a thin steel wire that we hook to a vise. So we have this thin circular steel wire, and we hook it into a vise and we pull on it with a force attached to one end. And we notice in this experiment that there is the wire itself has a length of 50 centimeters, and the radius of our thin wire is 0.001 meters. So it's 1 millimeter in radius, which is pretty big actually, but we notice that there's a fractional length change of 0.0002 meters. So 0.2 of a millimeter. And finally, the last thing that we need is Young's modulus for steel, for a thin steel wire, is 20 times 10 to the 10th pascals, which are newtons per meter squared. Okay. What we want to know is we want to know how much force would be required to do this. What is the force required to stretch this wire that much? And from what we had that Young's modulus was the stress over the strain, so the cross-sectional area over the change in length times L. If I solve this for F, I get that F is equal to E times delta L times A over L. And this is my cross-sectional area. So now all that's left, I have delta L, I have L, I have E, I need cross-sectional area A. If this is a thin circular steel wire, then this is pi r squared, which is pi times 0.001 squared. Okay. So now, really fast, one thing I want to do for you is scientific notation on this. So 20 times 10 to the 10th is 2 times 10 to the 11th. So this is 2 times 10 to the 11th. And the change in length is 2 times 10 to the minus 4. If I square this, I get pi times 1 to the negative 6th. So I get 1 times 10 to the minus 6 all over, and my length is 5 times 10 to the minus 1, okay? So 10 to the 11th, 11 minus 4 is 7, minus 6 is 1. So this becomes F is equal to 2 times 2 times pi over 5 times 10 to the 1 over 10 to the minus 1, and this minus 1 comes up, so it's 10 squared. That becomes 4/5 pi times 100. The minus 1 on the bottom becomes a positive 1 at the top. 10 squared is 100, and that answer is 251 newtons around them. Okay, so 251 newtons of force is required. That's not very much. I'm going to skip the next thing because it's a solution, but as you can see, this is basic plug and chug stuff here. There's nothing too tough about it. You need to know how to compute the area. You need to memorize this formula. Luckily, the formula is basically the same for all stress, strain, all that. So it says solution here, but what I want to talk about is actually the deflection. So imagine you had let me draw it this way. So we have a wire here, and it has some length, right? And then this is the original, okay? And we push it with a force. You apply a force, and there's some change in X, okay? This is known as shear. And shear is, the coefficient of shear is the force over the cross-sectional area still over the change in X, or the deflection, over the length. So this still has the same cross-sectional area if we were trying to bend our wire. And you would get that the force was the shear times the cross-sectional area times the change in X over L, which is just the deflection. It's exactly the same though. Instead of a length change, you're talking about a deflection curve. Everything else is exactly the same as what we just did. Nothing too major. Lastly, we have compression, and this is known as hydraulic stress, or compression. It's the volume change, it's the bulk modulus. And this was, the bulk modulus is the pressure, which is still force over area, divided by the volume change, okay? So this would be like a solid being dropped into the ocean, and at the bottom of the ocean, the pressure on every side of it would compress it and cause the volume to shrink. So what we see here is that the pressure is equal to this bulk modulus beta times the change in volume, or the fractional volume change. Pretty simple. There's all the physics is hidden in there. We're assuming that it's a solid object that you can compress. What I would like to talk about is imagining the volume change of a cubic meter of water, okay? We're going to find the fractional volume change over or at sea level for imagining what the volume of a cubic meter of water would be in space, in vacuum, and seeing what the fractional volume change is at the surface of the Earth and at the bottom of the ocean. So what we need to solve is we need the fractional volume change is equal to the pressure, P, divided by beta for water. And beta is the bulk modulus of water. The bulk modulus of water, it turns out, is about 2.2 times 10 to the 9th pascals. And again, pascals are newtons per meter squared. They're force over area. The pressure in space is 0, but the pressure at sea level is actually 1 times 10 to the 5th pascals. It's actually 1.01. I'm going to use 1. So at sea level, how much is the fractional volume change versus in a vacuum? And then the pressure at the bottom of the ocean is, we assume 4 times 10 to the 7th pascals. These are actual numbers, just so you know. So let's solve them. Let's find out what the fractional volume change is of water at the bottom of the ocean and at the surface of the Earth. So delta V over V for the pressure at sea level over beta. Pressure at sea level, we said, was 1 times 10 to the 5th. And the bulk modulus of water is 2.2 times 10 to the 9th. So this is 1 divided by 2.2 times 10 to the minus 4. If I multiply this whole thing by 100%, I get the percent change. And so I get 1 divided by 2.2 times 0.001. I get 0.0045%, okay? Which is very small. At the bottom of the ocean, so P at the ocean over beta is 4 times 10 to the 7th over 2.2 times 10 to the 9th. That is 4 divided by 2.2 times 10 to the minus 2. So 4 divided by 2.2 times 0.01 times 100 is 1.8%. So water at the bottom of the ocean has a fractional volume change. A cubic meter of water at the bottom of the ocean has a fractional volume change of 1.8%. Water's incompressible, which is why I wanted to show you this. We're going to talk about fluids in a couple weeks. And even though water is incompressible, that's a pretty big amount of pressure at the bottom of the ocean. It's enough to actually compress the water. So think about that. There's a kind of nice problem that's pretty hard in your book that they go through of a chair and some chair legs being compressed. I will tell you that I don't expect you to do that kind of analysis with the elasticity stuff. Generally what it comes down to is finding, say, the static equilibrium of a scaffold being held by a wire, and then being told, well, the tension, if the force on the wire is this much, it'll break. So find out like how much the wire stretches by or something. We'll go over that. You'll see that on practice exams. Elasticity is pretty fun. It's fun because it's plug and chug. The problem with it is, like I said, there's a lot of physics hidden in the bulk modulus and Young's modulus that you'll learn later on. If you really want to study this stuff as an engineer or a chemist, it's a very nice first approximation. And there's a lot more to the story of intermolecular forces and how solids stick together. That's basically my further notes on this. Overall, pretty fast, easy chapter. Do problems for it, do problems for it, do problems for it. I'll get you some problems, another set of problems for this week, but this is it for the material for exam 1. So my further notes would be, remember the 7 and 8 were energy, and 9 was momentum, linear. Chapter 10 and chapter 11 were basically torque, rotation and torque. So let's say this is rotation and torque, and this was angular momentum, and rotational energy, K, E, rotation. And then last was elasticity and equilibrium. So that's what's going to be on our exam 2. Probably going to have an energy equation or an energy problem. Might show up more than once. Problem where you need to use energy to determine the velocity of a system and how long it takes to fall, things like that. The linear momentum stuff was all impulse and collisions. So inelastic, elastic collisions, and then when we have a force applied over time, it changes the momentum. So what's the change in momentum? Those problems actually aren't too bad. They're pretty easy. Chapter 10 was all about rotation and an introduction to torque and how it works. Chapter 11 was a little bit of angular momentum stuff. It's what we did last week. And chapter 12 is this elasticity stuff. So it seems like a lot. You might feel a little bit lost, but once you see the practice exams, I think it's actually pretty easy stuff, assuming you've been doing your homework and reading your chapters and doing problems. But I'll get that practice exam to you, and I'll get you another lecture later this week doing some problems with elasticity. All right, hope you're all healthy and taking care of yourselves and your family and your loved ones. Talk to you soon. Bye.